Well, what we'd like is 3/4 times 1/2, not to return a decimal number in our system, but to return 3/8. Okay. So what we're going to do is we're going to create a system where we have some constructor called makeRat. Well, let me not define it yet. We'll define it later. We're going to have makeRat, which is going to take a numerator and a denominator and return some representation for a rational. For a rational number. Now, if we have this constructor, we're also going to need something called selectors. So this is the constructor. This is how we build it up. We need selectors, something to get the pieces out. In this case, we're going to have a selector called numer, which will return the numerator of x, assuming that x is a rational number built up by makeRat. And similarly, we'll have denom, which will return the denominator of x. Okay. Now, we've got this constructor. We've got these selectors. Let's just assume they work. Let's not even talk about how they work. You guys have been doing this already. You've been using schemes, primitive procedures without questioning what happens inside them, right? So let's just assume that we have this constructor, this selectors, and go with it. This is a data abstraction. Okay, this is a way for us to think about making rational numbers without actually knowing how they're represented internally in the system. Let's look at how we could write some code. We're going to add two rational numbers, n1 d1 plus n2 d2, not to be confused with r2 d2. Sorry. Not funny, not funny. n1 d2 plus n2 d1 over d1 d2. Okay. So let's write the code. And by the way, actually, the code that I'm putting up on the board today for rational numbers is in your book, in section 2.1. So we're going to define a procedure, add rat on x and y. Again, assuming that x and y are rational numbers. Okay, let's see. What do we need to do? Okay, so we're going to need to do some multiplications here. Okay, so what we've been looking at so far for the value we've been returning, we've been doing things like adding or multiplying. Here, what we want to do is we want to preserve the numerator and preserve the denominator. That bar is preserved by our constructor, makeRat. So we're going to make a rational out of, well, it takes a numerator and then the denominator. So what's the numerator going to be?
Numerator x times denominator of y.
Okay. So we're going to add those, right? So we'll take the numerator of x. Oops. Yeah. Numerator x, denominator y, 3, added to denominator of x. 1, 2, 1, 2. My prints get off a little bit there. Okay, so this is our numerator. We're going to add the result of multiplying the numerator of x times the denominator of y to the result of multiplying the numerator of y times the denominator of x. That's the first thing that we're passing to make rat. It needs one more thing, the denominator. The denominator is defined as the denominator of x times the denominator of y times denom x denom y. 1, 2, 3, 4. Questions? Okay. How do we define a rational being subtracted? Well, that's equal to d2 minus 2d1 over. Okay, so how do we write subrat? Okay, so I'm hearing it looks a lot like this, except we're going to change that. And for fun and excitement, since I know you guys had so much fun on problem set 2, you could write some sort of combine rat. But we're not going to do that here. Rat master, did I hear? The denom y, numer y, denom x, 1, 2, 3, times the denominator
The suggestion was you can define that by simply saying add rat x minus y.
Okay. Can we say minus y?
Not unless the interpreter knows what to do with that.
Right.
That'd be y minus something.
We don't know. Y is a rational number. And we have no idea how it's represented in the system. Okay? So, because of that, we don't know if we can just negate it. However, we could write a procedure to negate a rational. And how would we do that? So I'm going to define negate rat. It's only going to take in one rational number. You only negate one number. So we're going to, once again, make a rat out of, I hear, negate the numerator. Do I want to negate the denominator? No, because then I just make it positive again. So we're just going to say denom x. Okay, so now with negate rat, we could do define subrat xy, make rat, or rather, sorry, a call to add, starts with the letter A. Add rat of x negate y. Oh, sorry, negate rat. Questions on that? So we can't just put one of the primitive operators, plus, minus, multiplication, divide, and use those on our rational numbers because we need to be using our constructors and our selectors. We need to build it up with constructors, and we need to get the pieces of it using our selectors. Okay. Questions? How many hours of sleep did you guys get last night? Few? Not too many? Okay, let's do multiply rat. So n1 d1 times n2 d2 equals n1, rather, n1 n2 d1 d2. Define mult rat of x and y. Okay, what are we going to do here? All right, we're going to make a rat. We're going to return a rational number made up of two pieces. The first piece is, I hear numer x, denominator x. Is that what I want? Numerator y. Okay, so that's our numerator, and our denominator, similarly, denom x and denom y. Key. So, how could we do some math? How would I define a rational number? Let's say I want to define a rational number called 1/2. Make rat 1, 2. And if I wanted to define 3/4, do I care what make rat does? No. If you tell me there's a contract for these constructors and selectors, if you say this is how it works, I give you this to build it up, I give you this to take it apart, and you tell me that contract is going to hold, right? You know, like software engineering always works, right? In any case, if somebody hands me a contract and says this is how it works, I don't care what it does inside. Now, one could argue you kind of care what it does inside because you don't want them doing something really stupid that takes exponential time. But I don't really care what happens inside as long as they tell me this is how it's going to work. So now, if I wanted to multiply two rational numbers, let me define this to be the answer. What would I do? I want to multiply two numbers. 1/2 and 3/4. Mult rat 1/2, 3/4. 1, 2. Okay. Now, one thing we might want to do is give our user some way to print out a rational number. Because we don't exactly know how multrat is defined, and we don't know what representation we're going to be getting here. In fact, multrat could return some procedure. We don't know what it's going to do. So we need to write a procedure to print our rational number. Which we will call, I hear people whispering, print rat, print rat. Yep. A much better name. Much, much better name. But to stay with the convention in the book, we'll go with print rat. Guys are much funnier than I am. You win. Okay, so we want to print a rational number. So what we're going to do is use a combination of new line. I think we talked about this before. It's just going to go to the next line in our buffer. And then we can use the command display. Okay, so what do we want to display first? The numerator of x. Display takes in only one argument. So now we'll say display. Let's put in a division sign so it actually looks like a fraction when we spit it out. And then we'll display the denominator of x. So that's going to print out a rational number for us. So then, instead of having to define it to be something, we could just say print rat mult rat 1/2 3/4. Okay. And what would this print?
3/4.
I'll print out 3/8.
Are 1/2 and 3/4 written out longhand? Those are rational numbers.
We define them, variable names, to be rational numbers. No, Scheme is not smart enough to say, oh, 1/2, you must have meant. No, we had defined those up here and could have easily have been A, B, C, D, but for the sake of example, it makes a lot more sense to call them 1/2 and 3/4.
This structure, whatever it is letting it just name any variable and assign it to a rational number. Right?
In Scheme, we can name things using define. And we can name procedures. So if it was returning a procedure, we could name it.
I've just never heard of a data structure before. So.
Yes, actually, we haven't even seen a data structure before, right?
Thank you.
We haven't seen one before, and we haven't seen one yet. Because all we're looking at are these contracts, make rat, and then numerator and denominator. We don't even know what structure's underneath there. We have no idea how this is being represented in Scheme. It's often known as an abstraction barrier. We're being prevented from seeing the internals.
But we see how it works. It works just like a variable, right?
I mean, somehow it's pasting 3 and 4 together, right? So it could be writing a procedure. So makeRat takes 2 arguments and then returns a lambda expression. Or it could do something else. Yep.
I'm curious about the input for something like subrat xy. Is that where we put like subrat and we put in 1/2 and 3/4? What would you put in?
Right, so we would call subrat. We could also say, similarly, print rat subrat, and Bob Dole of the lecture. So we subrat 3/4, 1/2. We're going to get what printed? 1/4 will be printed. Okay. Yes?
The scheme doesn't have whole numbers, right? So we might end up, we do, for example, the division, we might end up with, that it's not 308, but 3, what, how do we make sure they come out as a whole number? Is there any kind of standard way of doing that? We're not dividing anything, so
We're not.
not in public multiplication, but when you do the division, you actually divide some numbers, right? So you might end up with coming out with something that's not whole numbers.
There's no division.
No, this is the multiplication, sorry. But
And actually, if you were dividing rat, there would be no multiplication either, because, yes, rather, n1 divided by d1 over n2 divided by d2 is equal to 1 d2 n2 d1. So we're not actually doing any division there either.
I I guess somehow,
But I think that the issue is a general one of rounding error, and that is an issue, and there are ways to get around it.
Wouldn't subret actually return 2/8?
Yes, it would. Very good. Why? Why is subret going to return 2/8? Well, actually, we don't even know, do we? It could return 1/4. It could return 2/8. Because we don't know what make rat does. We've been told make rat takes two numbers and makes them a rational number. Okay. Given that, I would make the assumption that it does not do the reduction. Because if it does do the reduction, they'll probably say make rat takes two numbers, finds the greatest common divisor, and then takes that out of it, returning a reduced fraction. Okay. Since we weren't told that, the likelihood is that's what will be returned. Okay. So, that said, let's figure out what make rat and numerator and denominator are. But before we look at that, let me talk about a new data structure, because that's what make rat, numerator, and denominator are going to turn out to be in this case. Okay, so we haven't seen any data structures. Today we're going to see what's known as a pair. And a pair has room for two pieces of data. And the data here can be numbers, can be variables, can be a procedure. Well, the variable will be evaluated, but it can be a procedure. Could be another one of these pairs. Okay, so pairs have the property of closure. Okay, so we can have a pair point to a pair. So how do we build a pair? In scheme, we use cons. Cons makes a pair. So if we were to say cons 1, 2, this is going to build a pair 1, 2. First cell points to the first element, second to the second one.
What are the pointers pointing to? Are they boxed internal representations?
This is just a notation for us to draw it on the board. It's called the box and pointer diagram. Okay, so internally, we actually don't know how it's represented. Okay. At least we're not going to talk about it right now. Okay, but on the board, we'll represent these as drawing them as box and pointer diagrams. Just like the substitution model, it's just a convenient way for us to try to picture what's going on here. And draw the box and pointer diagram. So let's actually define this to be A. So A is going to be bound to that structure. It's not a pointer, it's a binding. We draw it like this for convenience sake. Okay? If you guys have done C, it's not exactly like a C pointer. Okay? So we've got A pointing to 1 and 2. So that's cons. Now, given cons, given that we can build up pairs, we need some way to take them apart. Just like we had make rat, we then needed numer and denom. If we've got cons, we need some way to take out the pieces of the pair. So this part of the pair here, the first cell, this is known as the car of this pair. And this cell here, this is known as the cdr, CDR. Car and cdr. Just a common pronunciation for it. So let's say, given A, I want to get the number 1. How would I write that? I'd write car A, which will give me 1. If I'd like to get the 2, I would write cdr A to get the 2. Okay? Questions so far?
Do those things mean something?
Car and cdr, they're names for primitive procedures. They mean
CAR stands for Contents of the Address Register, and CUDR stands for Contents of the Decrement Register. This is a reference to the IBM 701 architecture, which is the first architecture on which Lisp was implemented. 704.
I like to say they stand for Primitive Procedures and Scheme.
So the cons, that's a primitive for just a two-element data structure?
So cons makes a pair, right? So you can think, it's called a pair, yes. It's two-element data structure, right? It's a pair. There's a first cell and a second cell. The first cell we get using CAR, the second cell we get using CUDR.
Do they have to be the same thing, or can they be different things? Like, do they both have to be numbers, or they both have to be procedures?
No. No, we can have anything be in those.
Cons only accepts two arguments. You could never, like, cons 1, 2, 3, 4.
No, but what we can do is we can chain them.
Sure.
Okay, so what we could do is we could define B. The reason I'm going to define it, it just makes it convenient when we write the CARs and the CUDRs to be able to have a name for it. So what we could do is we could cons, say the first cell could be a cons of 1 and 2, and the second cell could be a cons of 3 and 4. Okay, so what would this look like? Well, this is our top level pair. The first one points to this pair. 1, 2. And the second one points to this pair here. 3, 4. And then B is bound to that. I saw you both came up at the same time, so whichever one goes over.
What's the car of B return?
What's the car of B? Well, it's this here. The way that Scheme prints a pair is 1.2. So that's why Scheme that will print a pair. When you ask for the value here, the value it will return is 1.2 in parentheses. Yes?
This cascading con structure, that's not the end-all of these types of data structures.
Is there more than this? Is that what you're asking? At the basis of it, sure. We're going to see lists in the next lecture, but lists are just built up out of cons cells. We just build lists up from conses. We'll show how that breaks down.
If we wanted them to be actually joined, is that possible? Like the 1, 2, and 3, 4, the 1, 2, as we have it now, still remains a separate pair from 3, 4, which are within B, but like when we do the car of B, we get 1, 2.
Sure. How would we get the number 1?
The car of
The car of the car.
The car of the car, right? So you could say the car of B, and that would return 1. So could we join them? If you're asking, can we somehow create some massive structure like that? No. No, we can't do that. But what we could do is we could define it would actually print out paren 1.2 end paren. That's the way that it'll print out a pair. Okay. So what we could say is we could define C to be the cons of 1 to the cons of 2, the cons 3, 4. What this would look like is 1. We could draw this out this way if we wanted. 2, 3, 4. Okay. So this looks a little bit more like putting them sort of in a row.
So the car of C would then be 1.2.3.4.
No, the car of C is what the first cell points to. So the car here would be 1.
So how would you get the 1.2.3.4?
If you wanted it to print out, you could just have it, you could say C, and that would print out 1, dot 2, dot 3, dot 4.
It's a list structure or something.
It's not, well, yeah, okay.
It'll almost do that.
It'll almost do
I
that.
don't know why it won't.
I could talk about lists today.
You could talk.
We could talk about lists today. Let's talk about lists a little bit today. When scheme, when there's a dot and a paren like that, it doesn't actually print it. So it would say 1, 2. That one would go away. So that's actually how it would print out. Yep.
What's the cooter of C return?
What's the cooter of C? Well, the cooter is what's pointed to by this box. So that would actually print out 2, 3, dot 4, because there would have been a dot paren there. And that goes away. It doesn't actually print that. Let's finish a little more on car and cooter. We'll look at lists, because we're here. When you write car of the car, there's a shorthand notation for that. So car B can be written instead car of B. Subtle pronunciation difference. Scheme will understand that, and I believe it goes up to 6 in the middle here.
Boston invented that.
Sure, make fun of the natives. Okay. It's not ka, it's car. There actually would be an R there. And the Bostonians would not pronounce the R. It would be more of an H sound. Ka. It's your Boston pronunciation lesson for the day. Okay, similarly, let's say we wanted to pull out this pair. Let's say we want to pull out the 3. What would the 3 be? How would we get 3? Well, are we taking the cooter of the car or the car of the cooter? Well, first thing we want is this, right? That's the cooter. That's the first thing we do. So we take the cooter. So the cooter of B, that's what we take. And then we want to take the car of that. Okay? Which could also be written as catter. Okay. Pronunciation gets subtle as you add more A's and D's. You get cooter, various things like that. Yeah, pretty cool. This is a compression. Okay. You guys can make up all sorts of things about this. Here we almost wrote out a list structure. So let's just do lists today because we're here, and then we'll do more on lists the next class, which is tomorrow. I need board space. Everybody got this structure down?
If you just evaluate C, will it spit out that whole, will it spit out the parenthetical dot documentation thing? I mean, if you...
This is what it would print here.
And would you call C in parentheses or just C?
Would you call C in parentheses or just C? Why would we call just C and not put it in parentheses? Oh, it's not. We didn't write return a lambda expression. It's not an operator. It's not a procedure. So we don't want to apply it. We'll get an error if we try to apply it. Okay, list. As I alluded to a few moments ago, we have lists in scheme. And we can write list. And we could have written list 1, 2, 3, 4. List, if we wanted to draw a list, actually let me talk about the sugaring, then we'll draw it. List the sugars into cons, first element, 2 cons of the second element, 2 cons third, cons fourth, which would continue to go on. When we run out of elements, the last thing that is consed on is a nil, which is also sometimes represented as quote, open, close paren. 1. this would be drawn as, once you desugar it, it's easier to see how we would draw it. We've got a con cell. First one points to a 1. The second one points to another con cell, in which the first element is 2. And the next one points to another con cell that has the first element 3. Another con cell, first element 4. And the way that we denote nil in the box-appointed diagram is by putting a diagonal line through that last cell. Yes?
Is that an asterisk single quote for the parentheses?
No, that's just
Is that-
leftover.
Like, is
It
it, no,
has
no,
not
no.
an asterisk.
Is it the asterisk or not the asterisk? I'm sorry, the apostrophe.
Yeah, it's apostrophe. It's a single quote. Yeah. It's not the backwards one. It's the one that you would use if you were saying apostrophe S.
Thank you.
Okay. All right. So, yes, question?
Could you sugar your sugar list and just say cons 1, 2, 3, 4? You get the same result? Instead of saying list 1, 2, 3, 4, if I just said cons 1, 2, 3, 4, it would actually desugar the list, desugar it.
Cons takes 2 arguments. We've just given it 4. So this isn't going to work.
What if you put the 1 and the 2 in parentheses? Oh no, we're trying to evaluate it. So yeah, no, never mind.
Okay. There are ways of cheating for writing lists. Let's not go there today. Let's use for now, let's use list and cons to build up these structures. Okay, we'll see in a little while that we can use a shorthand cheat and not use these. But let's go with it for now. So if I wanted to get the number 3 out of this list, the car of the cooter of the cooter. And of course we have nothing defined here, so let's say that we actually define this to be something. 3. So the way we work on these, if we've got the multiples, or even if we don't have multiples, we work from right to left. So the first thing we do is we take the cooter. That's this guy. Then we take its cooter, rather, it's this guy. Should have drawn it quite so far. We take its cooter. And then we take its car. Okay. The 3. So this would actually, so we could expand this out as, we could write it out if you wanted to see it. Car, cooter, cooter, D. So the first thing we do is we take the cooter of D, which is what the second cell of our cons is pointing to, this part here. The next thing we do is we take the cooter of that, which is what the second cell of our that is pointing to, and then finally we take its car. 3.
So in general, to extract from list, it's always going to be one fewer D's, 1A and 1 fewer D's than the position of the thing in its list, in the list. So if you're
Sure,
doing
I guess you could think of it that way. Yeah, right, yeah. Right. But you can only put 6 in here. So after that, you'd have to start nesting more of them. But we'll see tomorrow that there are ways of manipulating lists that we won't end up writing these large strings of cars and cooters and things like that. What we can do is we can actually go through a list one element at a time. We can append things to lists. We can manipulate lists. We can multiply every element by 2, things like that. We'll do that tomorrow. Okay? Given that we have now seen con cells, let's go back to make rat. Usually after one stops talking about one topic to talk about another topic, it's because they're sort of related. So how could we define make rat? Now let's say we're going to define make rat x and y. cons x, y. Give me an alternative for what I just wrote. Anyone? We could say list, but I'm not talking about that actually. What I was suggesting, there are many alternatives as the answer. We could just define make rat to be cons. I don't have to build up the lambdas. We could do that. So, given that we've got this constructor, we should write our selectors. So we had numer on x is going to be the car of x, or alternatively, now, just subtlety about these. The book talks a little bit about why they choose to do it this way versus that way. If we define numer to be car, then basically what's going to happen is if we wanted somehow to step into tracing the list, we would be tracing into any car, whereas this would allow us to distinguish whether we were going into the numer of the car. That's what the book talks about. We haven't been doing any stepping. Actually, has anybody found the info file on stepping? No. So, in any case. But either of these are fine, given that we're not doing any stepping anyway. That's a little more elegant, actually. How would we write denominator? So we could write it one of two ways, denominator x, could x, or we could just define denom to be x. Rather, yes. If we define denom to be x, what would happen? Boom. We would have badness. Bad things. It wouldn't work right. Okay, so this is our, what do we call this? Constructor. And these are our selectors. Now we have broken the abstraction barrier. We know what they do. We've gone through that level. Before we were using them without knowing what they did. Now we've broken through that barrier.
Is that the only way to assign a value to like bar? Like if you look over here to on the board to the right, like the cooter of D was no.
The cooter of D is this structure here.
Let's say you had the bar the cooter, which was 3. How do you change that value to 5?
Someday.
You build a new list.
Yeah, we'll build a new list.
You build a new list.
We'll build a new list to do it. There are ways around that, but we're not going to get there right now. We're not going to do that. It's called mutation. We're not going to do it. We'll do it in a few days. Let's just go through the concepts.
Can you put cons in place of any two variables that a procedure takes? If it's a procedure that has two things, can you just write cons, or does it depend on what the procedure does? No, like make rat cons. Could I have, square cons? Well, square only takes one, but something that takes two things. Can I replace those two things with cons? Like sum.
Only if you want that to.
Define sum cons, something like that.
You could, but the behaviors, so basically what you're saying is if I have some procedure that I've been using, say sum of two squares, could I define the name sum of two squares to be cons? Sure. Are we going to return the sum of two squares?
No, you return that.
I'm going to return a pair.
Okay.
Okay, so certainly you can name cons anything you want, but you're probably not going to get the behavior that you're expecting to get out of it. Yep.
I don't know if you just addressed, what's the difference between a numer and a car?
Okay, numer was this data abstraction we had. And before we didn't know what numer was doing. Okay, here, once we've seen what it goes to, there actually is no difference, right? Numer is defined to be car. It does the same thing. Okay, but before when we were writing things, we had no idea what was going on internally. And that's what we call a data abstraction. It makes our code easier to read. Because when we were writing our procedures before, we saw that we were making a rational, of a numerator and a denominator. Now, if we were defining everything and we said, instead of make rat cons, and to get the numerator we said car, and get the denominator we said cooter, our code would have been a lot less clear. When you went to read your code, you would have been like, okay, I'm consing this and this. Whereas if we call them make rat, numer, and denom, it's much easier to read the code. You don't even need to know what's going on to see what's going to happen in that code.
But they're both primitives and they're both the same in the language?
Car, cooter, and cons are primitives.
Oh,
Now, we've
numerator.
defined numer and denom to be that, but they're not primitives. Yes?
I'm a bit unclear what form X and Y are going into make rat. And are they going in as like 5.63 and 3.75 and it's spitting out a rational fraction?
No. No. We're passing in the numerator and the denominator.
Oh, of one number?
Mm-hmm. Right, so that's what we saw before. We said, board. When we said define 1/2 to be a make rat on 1, 2. Okay, so we're passing in 2 integers into make rat, and it's just consing them together. So what would be the box and pointer diagram here? Well, it would have 1/2 bound to a cons cell where the first element were 1 and the second would be 2. So, in fact, make rat, unlike lots of languages, we're not doing any type checking here, right? Scheme doesn't do any type checking. We could have passed in something that had something after a decimal point. That's sort of violating what rational numbers are, what we're trying to do with this math system that we've just written up. But it could have been done. You know, it will happily cons them together.
So the purpose of this is now we can manipulate it. Now that it's in a data structure, we can use 1/2 with other things.
Right, we can now just say 1/2 and we go off and we can use this numerator, we can use this denominator, it's its own little happy cons cell living in memory. And we can use it, this pair is a data structure representing 1/2 together.
Now, if we were talking about earlier, if we wanted to, we could make rat more complicated by finding greatest common denominator.
Yep, let's do it. We can do it. Let me finish answering questions first. So I saw a couple of questions over here. Huh?
No, I guess my point is just, it's just perhaps slightly confusing. The X up there is probably, that's a whole number, why down there?
Sure, you could have called this make rat ND, cons ND, and here we could have said numer rat, or R, sure. Denom, R, cooter, R. Okay, that make it clear? Yep.
Is there anything that we can do to make our define make rat smarter so that when we plug things in there, we evaluate whether or not they're whole numbers, and if we're attempting to sort of make a rat with something that's not a whole number, spit out an error or something like that?
Sure. Let's do GCD first, and then we can do that. Let's define another make rat. Which I'm still going to call make rat. When you've got a constructor or selector and you're modifying that constructor or selector, do you want to give it a new name? No. If I were to change a name here to my make rat or smart make rat, what's going to happen to all that code I've written before? It's not going to call it, right? Because it's expecting to call a constructor called make rat. If we were to change a name, we'd have to change the code. That violates the data abstraction we're looking for, our extraction variable. What we're trying to do is say, I can write all this code regardless of the implementation of make rat. And make rat can change its implementation, and I don't need to change my code. That's a good thing. Data abstraction is good. We like data abstraction. And you'll love it after problem set 3. So let's make rat on the numerator and the denominator. I'm going to let G be the greatest common divisor of N and D. Then I'm going to cons what?
Divided by G. G divided by G.
Now we have a smart make-rat. It's going to reduce our fractions for us. So we're going to go spiraling off into larger and larger numbers that would reduce to something nice and neat.
Just assuming that GCD does something.
Yes, right.
Okay.
Assuming that we have a primitive called GCD that will return the greatest common divisor for us. Okay, so yesterday actually we had a question on the let, saying why would we want to use a let? So here's an example where let is going to save us from computing the greatest common divisor twice. By using our let, we only compute it once, and then we can use it twice. Okay, if we hadn't had a let, we would have had to write cons divide n GCD ND divide n GCD ND. Okay, and that's inefficient.
You could have just said, though, like, define G to be the greatest common denominator of N and D, right?
D.
Sure, we could have used a define, but a let is nicer, more elegant, the better way to do it.
Why?
Don't they essentially come down to the same thing after this?
No, they don't. Well, remember the let goes to.
Becomes a lambda. So it's defined now.
Define does not come down to be a lambda.
When you define it as a define,
Remember, define just creates a binding.
which has syntactic desugaring to a lambda. Well, it depends how you're using it.
If you define G to be the GCD of N and D, where's the lambda in there?
Not that one.
Right.
No. But if you do it to define it.
Define G and D as GCD and D. D sugar soup. Define G as a lambda and a D.
Sure, but there's no defining coming in our let. We're defining a lambda of G that will return, that will cons NG and DG. And then we apply that to GCD ND. There is no define there, and define has no lambda. All define does is bind this name to the value here. Now, what does the sugar? So if we said define g of x to be something, GCD x and 2, right? The define does desugar, right? So this is define G to be the lambda of x, GCD x2. Okay? But all define does is say, this is my name, and this is what I want it bound to. And so these are different. These aren't doing the same thing.
I think if you try to use define in this case, you would end up doing the same thing that you do with let.
Right. But it's not
Except
as
you
nice.
would be creating a superfluous binding.
Can you just point out where the variable, the expression in the body is in that let?
Okay. In this let, this is the variable list. Okay. Remember, the variable list takes the form open paren, and then each item in the list has an open paren, variable name, and the expression close. So this here is one item in our list, but we only have one item, So then it's surrounded by these outer parens. So that's the variable list. This is its body, which you can see over here. Here's the variable and its binding. Rather, it's what's going to get substituted in for it. And here's the body.
Okay, so G is sort of like just locally defined now? Or
G is local to the let. As soon as the let ends, as soon as we exit the body of the let, G goes poof. So if we had more stuff underneath here before we closed off make rat, G would be gone as soon as we closed off that let. If we were to do a define, G would be the two ways to do it.
Does this automatically take care of the multiplication case then? As we define multiplication before, will it automatically reduce? Because we use...
Our multiplication didn't do any reduction.
Well, but it
It called make rat, and then it would. The reduction would not come. The reduction wouldn't happen. It's not multrat. It's not anything we wrote in multrat that's doing the reduction.
You don't have to make any changes to multrat, or
No, right? Because this is the whole idea of the data abstraction that we have. Okay? Because we called it make rat, no matter what the implementation of make rat is, whether it's just a stupid cons or has smart GCD in it, multrat's going to do the same thing. Now we're going to see a different behavior. Okay, it will look different to us, right? Because it's either going to return 6/8 or 3/4. Okay, so we will see something different, but in a sense, it's behaving the same way. The constructor is still building up a rational, and the selector is still taking it out.
So for the define, you have a superfluous binding for the life of that
Procedure.
But in this case, that doesn't really make any difference because the procedure ends right after that. Right? Is that true? That the G
Right, the G would
be defined outside of make rat.
Right, it wouldn't be defined outside of make rat. It's just not as nice. No, is there any sort of dogma, any sort of official party line? I mean, it's just the let is the better thing to use because it's nicer, but I don't know. Yeah, it's easier to read it because when you see the let seems much more temporary, I guess, than reading a define. Certainly, if you're reading a define that's scoped inside of another define, you know. But let's say that somehow we got lots and lots of defines scoped underneath and it went over a page of code. It could be harder to read. This would be just a nicer way to write it.
My sense is more than just nice to read. The scope is going beyond what it really should be if you use it define.
Well, the question was in this case, right? In this case, there is no difference. But if we did have more code here, then we'd only want it scoped there. We wouldn't want it scoped to continue down.
That's really the primary difference beyond just this, what looks nicer. That's
Right, but in this case, there is no scoping difference. So in this case, it just looks nicer. But in general, if you had a bunch of, if you had some procedure, and then you did a bunch of defines here to get some local variables, but you only used it right here, and then didn't use it again in any of these statements going down here, then it would have been a lot nicer just to use a let for those, in that sense. Because otherwise, those variables are scoped down here. And actually, you could start getting some unintended behaviors, right? Because maybe you have lets that you're using locally here, but you also have some globals that you're trying to access out in the next thing. I guess something is to find the global environment down here. Yes? Okay. Alrighty. So. Let's define make rat another way. Okay. We could have defined make rat not in terms of cons. But make rat could have returned a procedure. So make rat on x and y could return a lambda expression. And we'll call our variable dispatch. So what's the body of our lambda? Well, we need some way to distinguish whether we've got a numerator or a denominator. So we're going to cond equals n0, rather dispatch, I'm sorry, equals dispatch. Okay, so if we pass in a 0 to this procedure, I'd like to return the numerator. Let me change these to n and d. I keep using x and y, I'm sorry. So if we have dispatch 0, I want to return the numerator. If it's 1, I'll return the denominator. And otherwise, I'm going to print an error. Why R1? Why R0?
I'm saying the body.
Huh?
I'm saying the body.
Oh. Okay, I'm sorry. I thought you were trying to tell me to define the variable name as R1. I'm like, but why? So you're trying to give me the actual answer. How about
Although it's 0.
R0, right. R, when we make a rational, it's a procedure object. It's a procedure object that takes in one argument. If we want to get the numerator, we pass in 0. So we take the rational, apply it to 0, and we'll get the numerator back. How about denom? Reminiscent of problem set 2, right? Okay. Could make rat, numerator and denominator be defined this way. When we wrote our code at the beginning of class, did we know? Did we care? Do we care once we write our code? It's the beauty of the barrier. We don't know, we don't care, it's there. We can use them. So we can define it as procedures instead of defining it as conn cells. Questions? Should we follow one of these through? Let's follow one of those through.
The purpose of this new make rat is to show how we can define it.
Purpose of this make rat, yeah, is just to show that we can define make rat in a number of different ways. Okay, so we can define it as just a simple cons. We can define it as cons once we remove the greatest common divisor, or we could define it as a higher order procedure.
And dispatch represents some code that you're using.
Dispatch is not code. Remember, dispatch is just a name of a variable that we're passing in. In this case, we're passing in a 0 or a 1. It's not code. It's just a number. Huh? It's a code, but it's not like it's a procedure.
Different sense of the word code.
Right.
Yeah.
Okay. So if we were to define, again, my favorite example, 1/2, to be make rat 1, 2. Okay, to do the define, we're going to bind this to what that evaluates to. So we need to evaluate make rat 1, 2. Okay, so make rat, let me be really formal here for the substitution model. Make rat is a lambda of 1 argument dispatch. And the body of that lambda is a conn statement. equals dispatch 0 n. Well, what happens? Does this n stay n? When we call makeRat with 1 and 2, we substitute in 1 and 2 for n and d. So it's not n here, but instead 1. Similarly, we'd have equal dispatch 1, 2. And then else error. This I will provide an ellipse on. Okay, so there's our procedure object that's returned from makeRat 1, 2. Okay? So this is what 1/2 is going to be bound to. Okay, so that's 1/2. 1/2 is bound to a procedure, right, a lambda expression. So if I call numer 1/2, what happens? Well, what does numer say we should do? We're going to evaluate the function that's being passed in, 1/2. I'm going to evaluate that with 0. So this is the procedure here. The 0 substitutes in for dispatch. Cond equals 0, 0. Yes, and it returns 1, the numerator. So what if we called denom? So if we call denom of 1/2, well, what does denom say that we do? We take 1/2 and apply it to 1. Well, this is 1/2 here. We substitute in 1 for dispatch. Is 1 equal to 0? No. Is 1 equal to 1? So we return 2, the denominator. Just an alternative representation for makeRat. Given the choice, we'd probably pick cons. However, we could do it another way, and we don't know. That's the whole thing about the data abstraction. We don't know how it's being done below. There are many different alternatives that we could have. So long as our selectors can pick the data out of what we constructed using our constructor, representation doesn't matter.
You couldn't, I mean, if you tried to say cons 1/2 or car 1/2 here, it would freak out.
Well, what if we defined our selector makeRat that way and then, oops, forgot, we did our constructor, we forgot to redefine the selectors. What would happen to us? We get errors, right? Because we try to apply, we try to do the car of R, and there's no car of a procedure, right? So we would have an error there. So if you do change the constructor, you need to change the selectors. Okay, let's say that again. You need to change selectors. If you change the constructors, you will be doing this in problem set 3. Yay. We should be playing blackjack. Fun. You have a good time. Any other questions? Okay, tomorrow we'll talk more about lists. Oh, sorry. Now there's a question.
About the quiz or any?
Anything about the quiz? Sure. It's an hour long. We'll have it be open book. Okay. So computer science is not about memorization, or at least programming isn't. I still find myself, not so much in Scheme, but certainly in C, pulling out my favorite copy of Koenig and Ritchie, which is like the little C Bible, and looking up syntax of various things that I don't use very often. Okay? It's not about memorization. You don't always know every single thing in the language, so it'll be open book.
Is it open book or can you use your computer?
You may not use your computers. It is not open computer.
Is it open notes?
Sure. Any written materials you can use, but you can't use a computer. Okay, so not be using computers, but you guys will see next to them, so don't be tempted. Okay? See you guys.